Alright, so solution to thermodynamic questions on the textbook. So over here we have a question that says, using equations alone, define the following internal energy. That is I, internal energy. So internal energy is equals to U, and we know that from the first law equation we have Q is equals to U plus W. Thermodynamic first law equation, U plus W. So if I know this, it means that U is equals to Q minus W, just like that. So I enthalpy. Enthalpy means heat, internal heat or heat of the system. So in that case, it means heat absorbed, when it's absorbed. So that means making the subject of the formula is the same thing as the first equation's law. So this is enthalpy, that is Q, or I can just say equals to H. Enthalpy is equals to U plus W. So this means the same thing, U plus W, U plus W. Now they say entropy, using equations, define entropy. So I entropy S, or delta S, change in entropy, is the same thing as Q over T. IV, the two laws of thermodynamics that deal with entropy. The two laws of thermodynamics that deal with entropy. The two laws of thermodynamics that deals with entropy is the second and the third law. So for the second law, is S is equals to Q over T. The second law states that for any spontaneous process, the total entropy of the system and surrounding increases. This is the formula. The third law says that it says, the way it stated it, the third law states that the entropy of a perfect crystal, that's the entropy of a perfect crystal, is zero at absolute temperature. Or you say at absolute temperature the entropy of a perfect system is zero, which is trying to say that it's not possible. So that this means that this is the sentence: S is not equals to zero at 0 Kelvin. At 0 Kelvin, or you say minus 273 degrees Celsius. This is the third law of thermodynamics. Now they say, using equation, define entropy change of the universe. Entropy change of the universe. So that is V, entropy change of the universe, delta S, entropy change of the universe, is equals to entropy change of the system plus entropy change of the surrounding. So that's number one. Solution to number one. Copy. Number two. Alright. Number two says, state the sign convention for A, Q for the amount of heat added to or removed from a system. Now, when heat is added to a system, absorbed, Q is positive. When heat is removed from a system, Q is negative. So when absorbed, added. When it is removed, released, is negative. Now let's move to the B part. 2B. There is no time. Copy. Now B, work. Now the sign convention for the amount of work done on a system. Show the sign. Is it positive or negative? Work done, for the amount of work done on or by a system. Now when work is done on a system, on a system, that is energy absorbed. When it is absorbing, it's positive. When work is done by system, when it's done on system, Now when work is done by system released by work is negative. Now they say number three, define the values of pure compounds as standard states for delta H. For delta H, that is enthalpy, heat of formation, enthalpy, heat of fission, and delta G, and delta S, or ZS. I talked about there. So C, B, and then E. Alright, so this is it. So define the values of pure compounds at standard states for delta H. So for pure compounds, that means pure elements. For pure elements, heat of formation, enthalpy can be 0 at STP. At STP. So oxygen, hydrogen, any of those compounds, any elements, any pure elements is said to be a pure compound. So when you have it, it's going to be 0 at STP. The same thing with Gibbs free energy, to be 0 at STP. But entropy, S for entropy, both entropy change, anything entropy cannot be 0. It must have a value, and the value is always given, or you look it up from the table. So this is the answer. It must have a value, must have a given value in the question. So then let's move to number 4. Number 4 says, at high enough temperature, how does entropy and enthalpy vary with each other? At high enough temperature, how does entropy and enthalpy vary with each other? At high enough temperature, entropy, temperature, the very high degree of disorderliness, when it's very high, extensively very high, that it can't be overlooked, entropy tends to dominate. Yes, entropy tends to dominate. So it tends to dominate. So at high enough temperature, entropy dominates enthalpy. All right. So moving to the 5th one. So how you do this kind of video is you take your time, watch it because it's part of it. Moving to the 5th one, they said find delta H, delta S, find enthalpy change, entropy change, and Gibbs free energy, change in Gibbs free energy in one sentence for each. And in one sentence for each, describe the implication of these values. Describe the implications of these values. They gave me nitrogen oxide. Now they are telling me to find the implication of value. You should mind yourself. So you can read. Yes. So solving this question, I'll have that this is the given value. This is the value I'm giving. NO plus half O2, looking at it. And I'm giving values for the entropy and the enthalpy. So solving this, I can still balance the equation in another way. Can balance this in another form so that I have this way, whichever way. The one given is balanced, but I can still balance it this way if it's confusing you. So if I've balanced it, they said I should find enthalpy change. And if you solve, enthalpy of products given is 240 minus 90 plus 0 for oxygen that is alone, pure element. Now when you do it, you have 150.5 kilojoule. Then moving down for entropy change, Moving down for entropy change, we have that this is 240.5 minus 211 plus 205. When you solve, you get minus 175.5 kilojoules. So I've solved it already. Now for the Gibbs free energy, now look at what I wrote there. I said when T not given, use T is equals to 25 degrees C, which is the same thing as 298 Kelvin. So Gibbs free energy is the same thing as delta H minus temperature times change in entropy. That's Gibbs free energy. That's energy that tells us more or much better, much convenient whether a reaction will occur or not. So we have 150.5 for enthalpy, then 298 Kelvin temperature, then entropy, then we times it by 1 kilojoule over 1000 joules so that we can convert joules to kilojoules, which is the unit of energy for Gibbs free energy. So when you do this very well, you have that this is 150 and 150.5 plus 52,299, and solving further you get this value. Then it will be good enough you know this table, delta H, delta G. So when the sign of delta H, enthalpy is positive and Gibbs free energy is positive, reaction will occur. When it's negative, reaction will occur. Now when it's positive, negative for enthalpy and Gibbs free energy, reaction will occur if temperature very high. The same thing if the enthalpy is negative and Gibbs free energy is positive, reaction will occur at lower temperature. Then for the universe, table 2, when we have entropy of the universe against Gibbs free energy, when entropy of the universe is positive and Gibbs free energy is negative, it means increase in spontaneity. It means for it to be negative means that it is not being affected by the universe, so it is negative, is happening on its own, so reaction will occur. Now when it's 0 and this is 0, no change will occur. And remember we told you that entropy tends not to decrease, but any decrease or anytime you see negative value for entropy, it means that it's decreasing, which is not normal, because entropy is supposed to be on the increase or at equilibrium. So but positive value means that your entropy of the system is increasing. So when it's negative and this is positive, it means decrease, not spontaneous, not occur, will be reversible reaction. So there you have it. Please like, share and subscribe. If there's any question, you drop your comments. This is Academic Daddy. We are gearing towards exam period and I'm trying to see if I can get as many videos posted as possible. I love you guys. I really love you guys. I just told people, show me back down love. I'm taking whatever we are doing here very, very serious. Thank you very much.